What is the bubble point of a membrane oxygenator? A. The temperature at which the priming fluid boils. B. The pressure at which gas is forced through the pores of a wet membrane. C. The number of bubbles allowed in the venous reservoir. D. The speed of the pump required to remove air. Answer: B. The pressure at which gas is forced through the pores of a wet membrane. Explanation: the bubble point is the pressure threshold where gas can pass through the membrane fibers into the blood compartment. During priming, it is vital not to exceed this pressure, usually by keeping gas flow off or low, to prevent air from being forced into the wet blood side. In a gravity prime, the priming bag is hung high above the circuit to A. Increase the speed of the pump. B. Use hydrostatic pressure to push air out of the fibers. C. Prevent the heat exchanger from leaking. D. Calibrate the flow sensor. Answer: B. Use hydrostatic pressure to push air out of the fibers. Explanation: gravity priming uses the weight of the fluid column to create enough pressure to displace air from the tiny spaces within the oxygenator fibers. It is often a slower, more controlled method than using the pump to prime. Why must the heat exchanger be tested for leaks during the assembly phase? A. To ensure the blood doesn't get too cold. B. To prevent water from the heater-cooler unit from leaking into the blood path, or vice versa. C. To check if the pump head is spinning. D. To calibrate the SVO2 probe. Answer: B. To prevent water from the heater-cooler unit from leaking into the blood path, or vice versa. Explanation: the heat exchanger contains a barrier, usually metal or plastic, between the blood and the water from the heater-cooler. A leak here is a catastrophic failure that can lead to hemolysis, water intoxication, or sepsis. Which of the following is a specific risk when priming with 5% albumin? A. Excessive foaming if the circuit is agitated or tapped too aggressively. B. The solution will freeze in the heat exchanger. C. It causes immediate clotting of the pump. D. It turns the priming fluid opaque, hiding all bubbles. Answer: A. Excessive foaming if the circuit is agitated or tapped too aggressively. Explanation: albumin is a protein. If the circuit is recirculated at high speeds or shaken during de-airing, it can create a protein foam that makes it very difficult to see and remove remaining air bubbles. What is the purpose of recirculation after the circuit is fully primed but before the patient is connected? A. To wear down the pump blades. B. To ensure a uniform temperature and a final scrub of any microscopic air. C. To deplete the oxygen in the priming bag. D. To increase the pH of the crystalloid to 8.0. Answer: B. To ensure a uniform temperature and a final scrub of any microscopic air. Explanation: recirculating the prime through the bridge allows the fluid to reach a steady state of temperature, usually 37 Circ. And gives the specialist a final chance to catch any microbubbles that might have been trapped in the oxygenator fibers. When assembling a circuit for a pediatric patient, why is circuit volume more critical than in an adult? A. Smaller circuits have more air. B. The ratio of prime volume to patient blood volume is much higher, risking extreme hemodilution. C. Pediatric pumps don't use centrifugal force. D. Pediatric tubing is much thicker. Answer: B. The ratio of prime volume to patient blood volume is much higher, risking extreme hemodilution. Explanation: in a neonate, the circuit volume might be 2 to 3 times the baby's total blood volume. This requires a much more precise blood prime, adjusting hematocrit, pH, and electrolytes to avoid a prime shock upon connection. Which component is usually the last to be de-aired in a standard circuit? A. The pump head. B. The venous line. C. The pressure monitoring lines/pigtails. D. The oxygenator gas phase. Answer: C. The pressure monitoring lines/pigtails. Explanation: pigtails and pressure lines are dead-end tubes. Air easily gets trapped in these small bore lines and requires manual aspiration with a syringe, whereas the main circuit uses the bridge for bulk de-airing. What does a negative pressure alarm on the venous side during priming indicate? A. The priming bag is empty or the venous line is kinked. B. The pump is spinning too slowly. C. The oxygenator is full of air. D. The heat exchanger is too hot. Answer: A. The priming bag is empty or the venous line is kinked. Explanation: if the pump is spinning but cannot pull fluid because the source, priming bag, is empty or blocked, it creates a vacuum. In a clinical setting, this chatter can cause hemolysis or vessel collapse. During a blood prime, why is the pH of the prime checked and adjusted? A. Stored blood is often very acidic, low pH, due to preservative solutions and CO2 buildup. B. To make the blood more viscous. C. To prevent the pump from rusting. D. To ensure the oxygenator doesn't leak. Answer: A. Stored blood is often very acidic, low pH, due to preservative solutions and CO2 buildup. Explanation: stored PRBCs can have a pH as low as 6.6. Adding this directly to a sick patient could cause a cardiac arrest. Specialists add sodium bicarbonate to the prime to bring the pH toward the physiological range of 7.4. What is the wet-to-wet connection technique? A. Connecting the oxygenator to the pump under a faucet. B. Connecting the prime circuit to the patient's cannulae while ensuring both ends are overflowing with fluid to exclude air. C. Cleaning the floor after a leak. D. Priming the circuit with water before using saline. Answer: B. Connecting the prime circuit to the patient's cannulae while ensuring both ends are overflowing with fluid to exclude air. Explanation: this is the most critical step of the connection phase. By creating a convex meniscus of fluid on both the circuit connector and the patient's cannula, the specialist ensures that no air is trapped inside the junction when the two pieces are pushed together.